Hello everyone, in this video we are going to talk about the isomers of C3H6O. Let us first determine the degree of unsaturation to know whether it is a completely saturated elemental composition or not. Degree of unsaturation for this elemental composition is equal to 1 plus number of carbon atoms minus number of hydrogen atoms by 2. Oxygen atom doesn't participate in the degree of unsaturation calculation. Therefore, we don't have to worry about that. This means 1 plus 3 minus 6 by 2. Therefore, 4 minus 3 and that is equal to 1. This means the structure can either have a carbon-carbon double bond or it can also have a carbonyl group. That carbonyl group could either be an aldehyde or it could be a ketone. Both the possibilities are there. Or it can also have a ring structure. Either it could be a 3-membered ring. I am just not drawing the hydrogens here, just to show you what kind of ring structures are possible. Or the ring structure can have 2 carbons and 1 oxygen. So it's a cyclic ether. Or it could be a 4-membered ring with 3 carbons and 1 oxygen. So all these possibilities we need to explore. Let's do this one by one. We are going to divide the isomers in terms of functional groups. Let us first write down aldehydes and ketones, so that is somewhat easier to remember. Aldehydes or ketones. Number 1, we are going to write propanol, that is CH3, CH2, C double bond O, H. The IUPAC name for this molecule is propanol, and the same in bond line notation would be 1, 2, 3 and then carbonyl group. Now keep it in mind that sometimes people leave it at this stage. Sometimes people write hydrogen. If hydrogen is not mentioned, that doesn't mean that it is a ketone. It is an aldehyde. Hydrogen is just not written there. They have hidden the hydrogen atom too. So both are one and the same. Both are propanol or propionaldehyde. They are one and the same. It's just the representation can differ sometimes. It doesn't mean that one is a ketone, another is an aldehyde. Both are aldehydes. In higher level organic chemistry courses, you might see structures like this instead of putting the hydrogen explicitly. And the other thing that you need to remember is aldehyde is a terminal functional group. It would always come at the end. If a carbonyl group is mentioned at the end, it means that it is an aldehyde, because ketone is not a terminal functional group. Ketone always has to come in the middle. So let's write a ketone, that is CH3, C double bond O, CH3. This is a ketone. So what we have is acetone, that is a common name, and the systematic IUPAC name would be propane 2,1. Sometimes it's okay to leave the number 2 also. We can simply mention it as propanone, because there is only one way you can number it, isn't it? Whether you number it from left to right or right to left, it would be one and the same. So therefore leaving this number 2 is completely okay, and mentioning it as propanone means that it is indeed acetone. And the corresponding structure in bond line notation for propanone would be this one. Let's move to alcohols. Number 3, we are going to write allyl alcohol, that is H2C double bond CH, CH2 OH, and the corresponding structure in bond line notation would be 1, 2, 3 and then the OH group, and then the double bond between 2 and 3 position. So how do we number this molecule? In this case, we have to number it right to left because our functional group is here. Therefore, we have to number right to left. If we number left to right, that would be wrong. So for example, if we number it this way, in that case we are giving high priority to the alkene and low priority to the functional group, and the IUPAC name would become prop 1 in 3 all. Is that correct? No, it is not correct. Let me remove this. So therefore, this way of numbering is wrong. This way of numbering is correct. And the IUPAC name is prop 2 in 1 all. That is the correct IUPAC name. And this group is called allyl group. So therefore, the common name is allyl alcohol. The difference is you have an extra CH2. This is vinyl alcohol. Compared to vinyl alcohol, we have an extra CH2 here. So that's why it's called allyl alcohol. That's a common name, but the proper IUPAC name is prop 2 in 1 all. And also cis-trans isomerism is not possible because on one side of the double bond we have 2 hydrogens. So therefore, no geometrical isomerism is possible for prop 2 in 1 all. Let's move to number 4. We are going to write cis prop 1 in 1 all, that is H3C, CH, and then double bond, and then COH, and then hydrogen. Now if we assign priorities as per the Kohn-Ingold-Prelog rules, then this gets the top priority because atomic number of oxygen is higher than the atomic number of hydrogen. This gets the least priority. On this side too, hydrogen gets the least priority, carbon gets the top priority. Our higher priorities are on the same side. Let me number it 1, 2, 3. So the IUPAC name for this molecule is in parenthesis 1Z because we have priorities on the same side. If the higher priorities are on the same side, then it is a Z isomer. If it is not on the same side, then it is a E isomer. So this is a Z isomer. So in parenthesis 1Z and then prop 1 in 1 all. And the same structure in bond line notation would be 1, 2, 3 and then the double bond between 1 and 2. When I write the structure in bond line notation, I say 1, 2, 3, but that 1, 2, 3 refers to the number of carbon atoms. It shouldn't be confused with the numbers here. Okay. I just don't want to miss carbon atoms. That's why I say 1, 2, 3 when I write the structure. And then number 5, we are going to write the trans isomer. So this is a cis isomer. Normally you would be writing the name as cis prop 1 in 1 all. But as I mentioned, I prefer the EZ convention. So therefore this is a proper way of writing name, because when you have 4 different groups, then the cis-trans convention will fall apart, and that's the reason I follow EZ convention. And then let's write the trans isomer. So hydrogen would be on the opposite side. So this means HC and then H3C on one side, and then on the other side we will retain everything as it is. So now the priorities are on the opposite side, isn't it? Higher priorities are on the opposite side here. So therefore this is a E isomer. 1, 2, 3. And the proper IUPAC name for this molecule is in parenthesis 1E prop 1 in 1 all. And the same structure in bond line notation would be 1, 2, 3 and then the OH group and the double bond between 1 and 2. Let's move to isomer 6. So number 6 we are going to write prop 1 in 2 all. Therefore the OH group is at its second position now. It is in the middle. H, C, H, double bond and then COH and then CH3. In this case we have to number left to right. That is the correct way of numbering. Why? Because if you number it right to left, what will happen? Then the position of alcohol won't be affected, but the position of the double bond will be affected. You will be giving a higher number for the double bond. So therefore, that way of numbering is incorrect. This is the correct way of numbering, isn't it? So prop 1 in 2 all, not prop 2 in 2 all. That is incorrect, isn't it? So therefore, that's not the way we should number it. We have to number it left to right here. Let me remove this. And the corresponding structure in bond line notation would be 1, 2, 3, and then the double bond, and then the OH group. No geometrical isomerism is possible in this because on one side of the double bond we have same atoms, 2 hydrogen atoms. So therefore, no geometrical isomerism. And then number 7, we are going to write cyclopropanol, that is CCC. So we have the 3-membered ring, and then hydrogen, 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 and then here 1 hydrogen and then 1 OH group. And the same thing in bond line notation would be like this. This is cyclopropanol. No need to mention it as 1 cyclopropanol because wherever you put the OH group, that is 1. Therefore, no need to specify 1 here. Simply mentioning it as cyclopropanol will suffice. Now we are exhausted with the alcohols. Let's move to ethers. Number 8, we are going to write 2-methyl oxyrene, that is oxygen, carbon, and then carbon, and then 1 methyl group at 2 position, and then 1 hydrogen where the methyl group was connected. So this is 2-methyl oxyrene, but this carbon atom is chiral because we have 4 different groups around it, isn't it? We have a hydrogen, we have a methyl group, and then on one side we have CH2, and then on the other side we have oxygen. So whenever a carbon atom or a heteroatom is connected to 4 different units, then that atom becomes chiral. So therefore, R and S configuration is possible. Therefore, the IUPAC name for this molecule is either in parenthesis 2R methyl oxyrene or 2S methyl oxyrene. Both the isomers are possible because we have a chiral center. And the same in bond line notation would be this way. Or if you want to mention the RS configuration, then you can write it this way. And the common name for this is 1,2 epoxy propane. That is a common name. Or sometimes people also mention it as propylene oxide. Alright, let's move to number 10. Because we had 2 isomers for the previous one, I am writing it as number 10 instead of number 9. We are going to write 1,3 propylene oxide. That is oxygen connected to carbon, carbon, and then another carbon. So we have a 4-membered ring with 3 carbon atoms and 1 oxygen atom. And the same thing in bond line notation would be this one. So this is 1,3 propylene oxide, or sometimes people mention it as 1,3 epoxy propane. But the preferred IUPAC name for this molecule is oxetane. That's the preferred IUPAC name. These two are common names. This is the preferred IUPAC name. Let's move to number 11. We are going to write methyl vinyl ether, that is CH2 double bond CH and then O and then CH3. So this is methyl vinyl ether. That's the common name. But the IUPAC name is methoxy, because we have the methoxy group here. Methoxyethene, not ethane, ethene, because we have the double bond here. So therefore ethene. And the same in bond line notation would be 1, 2, and then the oxygen atom, and then the methyl group, and then the double bond. That's the corresponding structure in bond line notation. So in total we have 11 isomers, constitutional plus stereoisomers, that is equal to 11 for this elemental composition. But if they are asking only constitutional isomers, then we have to consider it as 9 isomers. Why? Because here we have to count it as one isomer, because we counted it as 2 isomers. But when we count it only as constitutional isomers, then we have to count this one as one isomer, and then we had geometrical isomerism for this one. That also needs to be counted as one isomer. That's the reason if they are asking only constitutional isomers, then the answer has to be 9. But if they are asking constitutional plus stereoisomers, then the answer should be 11. So you need to see in the question paper what kind of thing they are asking. If it is constitutional, then the answer should be 9. If it is constitutional plus stereoisomers, then the answer should be 11.